Now that we've introduced inverse functions, it's helpful to understand how we can determine if they exist. Well, one of the big things is that the function has to be one-to-one. So one-to-oneness is kind of a rigorous definition, but what it really means is that each output has a unique input. What does that mean? Well, that means that if I tell you that the function output at A is 4 and the function output at B is 4, then what I'm really telling you is that A and B are the same number. You essentially can't have two separate inputs that have the same output. So if f of 1 is 3, then f of 2 cannot be 3. F of 10 cannot be 3. It's the only one that's tied to that output. So it's 1-to-1. One input to one output. Now, a lot of times we use what's called this thing called the horizontal line test. You know, if you go back and remember, a lot of people remember the vertical line test to test if something is a function. And the horizontal line test is basically the same thing. It's just testing a line horizontally. If it strikes at more than one point, the function can't be one-to-one. An example is like this one. So notice that if this height was 2, for instance, then if you plugged in this number and that number, you'd get the same height. So therefore, that horizontal line test at some point will strike more than one point on the graph. So it fails. This function does not have an inverse. This function does have an inverse. Even though it has that little curvature change and everything, there's never a point where a horizontal line would strike through and catch it. The issue that you have with the horizontal line test, there's really two. The first one is that the graph is a pretty poor estimate for what a function actually is, because sometimes functions have small variations that are difficult to notice or kind of inscrutable from looking at it, trying to figure out how to understand it. The second one is that you would, in theory, have to draw a line everywhere. So if I took this function and I drew a line here, I'd have no problem with the horizontal line test. But if I drew it here, I strike at 3 points, causing it to be a failure. So you have to be careful of your choice of line. And for sort of the classical polynomial functions and whatnot, that's not as big of a deal. But if you deal with more complicated functions, it can be problematic to try to use something like the horizontal line test. Either way, it's still a good starting place for what you're doing. If we want to be a little more rigorous here, though, we can start talking about functions being monotone, specifically being strictly monotone. A function is considered strictly monotone if on some interval, so if it's strictly monotone on an interval, it's either always increasing or always decreasing. Now, a function can be called monotone if it's increasing or constant, and it can be, or if it's decreasing or constant. But if it's strictly monotone, it's increasing the whole time or decreasing the whole time. But we know from our studies in calculus already that if the function has a derivative, and that derivative is defined on that interval, if we find that the derivative is either positive or negative the entire time, it can't change. So if it's either positive or negative for each value in the interval, so if it's always increasing or always decreasing, that tells me that it is strictly monotone on that interval. Well, if it's always increasing, look at a function kind of like that. There's no way that you're going to get this type of behavior because to get that kind of behavior, it has to go up and come back down, or it would have to plane off, and by this definition, the derivative can't be 0, so it never planes off. So you always have this increasing behavior. You could have a kind of a decreasing behavior, but in this particular case, we're not showing any of that. But anyway, if you can guarantee monotonicity, strict monotonicity, you can guarantee an inverse. Now, I was a little bit tricky here because I noticed I said that was on an interval. I didn't say over the entire domain. Now, if it's over its entire domain monotone, you know that it has an inverse. But there's a second thing. You can define inverses on subdomains. You can say things like, oh, I only want to look at this half of the graph. So if you define a function where on this half of the graph it looks like you're only defining the domain for like positive numbers, this function, this sub-function, has an inverse because it would be strictly monotone decreasing on the entire set. So we have to be careful with that. A really good example of that is like the square root of x and x squared. So x squared doesn't have an inverse because the horizontal line test doesn't pass on that. But if you constrict it or restrict it to 0 and positive numbers, then x squared always goes up like that. And so it does have an inverse, which is the square root of x. And notice that the square root of x, its domain is only positive numbers, and its range is also only positive numbers, or non-negative numbers. And if you restrict that x squared to that, you will also have a domain of non-negative numbers and a range of non-negative numbers. But I don't want to pack too much into this video, but essentially this is the whole point. You take the derivative and check. So let's take a look at two examples here. If I take the derivative of this function, I get 3x squared minus 6x plus 3. At which point, I then can factor out a 3. I get 3x squared minus 2x plus 1, which I can then rewrite as 3x minus 1 squared. So what I notice here is that no matter what I plug in for x, this function is always positive or 0. So this function has a momentary point where it would plane off, but it is generally increasing. So you have to be a little bit careful at one. You say, oh, is it constant? Well, it's not. It's never actually constant there, because for something to be constant, it has to be 0 kind of across an interval. It can't just be at a single point. What this is going to be is a stationary point. It's actually you're going to find it's going to have like a inflection point there because it's a cubic function. So this function's okay. This one is always increasing. So since it is always increasing, this has an inverse. This is guaranteed an inverse. Now over here, if I take this thing's derivative, f prime of x is 2 sine of x cosine of x. And you might say, well, that's squared. That's always positive. Yeah, it's always positive. It doesn't mean that it's always increasing. So if I have this, well, sine of x times cosine of x, this could also be written as sine of 2x, which is probably a better way to write that. If you write as sine of 2x, well, that's just the same graph as sine of x, but you have a decreased period. So it's kind of smashed in. So since you have that, it's got that wave behavior. Well, that's going to fail the horizontal line test. So this function does not have an inverse unless you restrict its domain to a very specific band.